For this problem on the topic of gravitation, we are told that a curve of a radius 78 meters is banked for a speed of 85 kilometers an hour. The coefficient of static friction is 0.3, and we want to know the range of speeds that a car can have to make this curve safely. Now, since the curve is designed for a speed of 85 kilometers an hour, traveling at that speed would mean no friction is needed to round the curve. And the no friction banking angle is given. So this is when v is equal to 85 kilometers an hour. The angle theta is equal to the arctan of v squared over rg, which is the arctan of 85 kilometers an hour multiplied by the conversion, a meter per second, is equivalent to 3.6 kilometers per hour, and all the squared, divided by the radius, 78 meters, times the acceleration due to gravity, 9.8 meters per square second. This gives us the angle theta to be 36.1 degrees. If we drive at a higher speed, v is greater than 85 kilometers an hour, and the radius remains constant, that means more centripetal force will be required than is present by the normal force alone. The extra centripetal force will be supplied by a force of static friction, which is downward along the incline, as we can see in the first free body diagram. Now we can write Newton's second law in both the x and y directions, and the car will have no acceleration in the y direction and centripetal acceleration in the x direction. We also assume that the car is on the verge of skidding, so that the static frictional force has its maximum value, FFR, is equal to mu s times Fn. And so the sum of the forces in the y direction is equal to Fn cosine theta minus mg minus the vertical component of the friction, FFR, times sine of theta. And this is equal to 0 for the car on the verge of slipping. And this implies that Fn times the cosine of theta minus mu s times Fn times the sine of theta is equal to mg. So this normal force Fn is equal to mg divided by the cosine of theta minus the coefficient of static friction, mu s, multiplied by the sine of theta. And if we do the same for the horizontal component of forces, the sum of the forces in the horizontal direction is Fn sine of theta plus the frictional force FFR times the cosine of theta. This must be equal to the centripetal force mv squared over r. So this means that Fn is equal to mv squared over r all divided by sine theta plus mu s cosine theta. Again, if we replace FFR by mu s times n. So now we have two expressions for the normal force Fn, which we can equate and solve for the speed. So we have mv squared over r all divided by sine theta plus mu s cosine theta is equal to mg divided by cosine theta minus mu s sine theta, which means that by rearranging we get the speed Vmax to be the square root of r times g times sine theta minus mu s cosine theta divided by cosine theta minus mu s sine theta. And so if we substitute our values into this, we get this to be the square root of 78 meters, we'll suppress the units, times 9.8 meters per square second times the sine of 36.1 degrees plus 0.3 times the cosine of 36.1 degrees divided by the cosine of 36.1 degrees minus, this is a plus in the numerator, so that's divided by the cosine of 36.1 degrees minus 0.3 times the sine of 36.1 degrees. And so calculating, we get the maximum speed to be 31.73 meters per second, which is approximately 32 meters per second. And so this is 110 kilometers per hour. Now, for the slowest speed possible, driving at a slower speed with the same radius means that less centripetal force will be required than that's applied by the normal force. That decline in centripetal force will be supplied by a force of static friction, which now acts upward along the incline, as we can see in our second force diagram. Again, we'll write Newton's second law in both the x and y directions, and the car will have no acceleration in the y direction and centripetal acceleration in the x direction. Again, we'll assume that the car is on the verge of skidding, and so Ffr is equal to mu s times the normal force Fn. And so by Newton's second law, again, we have the sum of the vertical forces is equal to Fn cosine theta minus mg plus the frictional force Ffr times the sine of theta, and this must equal to 0, which means that the normal force Fn, again, we substitute mu s Fn for the frictional force, and we get this to be mg divided by cosine theta plus mu s sine of theta. Now, if we take the resultant horizontal component of the force, we get Fn sine of theta minus the frictional force Ffr times the cosine of theta, which is responsible for the centripetal force mv squared over r. So again, we can rearrange and solve for the normal force Fn. We get Fn to be mv squared over r divided by sine of theta minus mu s cosine theta. And so we have another expression for the normal forces. Therefore, again, if we equate these two, we have mv squared over r divided by sine theta minus mu s cosine theta must equal to m times g over cosine theta plus mu s sine of theta. So rearranging, we get the speed v, which is the minimum speed v min, to be the square root of r times g multiplied by sine theta minus mu s cosine theta divided by cosine theta minus mu s sine of theta. Again, all these values are known, so we can find this minimum speed. And so this is, again, 78 meters into 9.8 meters per square second into the sine of 36.1 degrees minus 0.3 times the cosine of 36.1 degrees divided by the cosine of 36.1 degrees minus 0.3 times the sine of 36.1 degrees. And so calculating, we get the minimum speed to be approximately 16 meters per second, which is 59 kilometers an hour. So therefore, the range of speeds that can be safely traveled by the car on this embankment is 16 meters per second less than equal to v less than equal to 32 meters per second, which is a speed of between 59 kilometers per hour and 110 kilometers per hour.